Welcome also from my side. It's a big pleasure to see such a big crowd here in the audience. I've never seen this room so full recently. It is my pleasure today to tell you a little bit about planetary host stars and their output and evolution, which is crucial for the habitability of exoplanets for the Earth and for planets around other stars. Planets form in protoplanetary disks around young stars, and the subject of my talk is the stars. I will focus on that. Of course, there are disks and interstellar media where stars are formed, but this will be the subject of Bruce Elmgreen's talk tomorrow. Originally, his talk was supposed to be before mine, but he couldn't make it for today in the morning, so his talk was shifted to tomorrow. And Inga Kamp, right after me, will talk about the physical and chemical properties of protoplanetary disks. Just to put my talk into context, I will focus on the star as soon as it has lost its disk already and is influencing the planets around it. So when we talk about stars and want to look for planets around them, we mostly focus for various reasons on only specific type of stars. We don't really take into account O stars and A stars because they are too short to develop any biology around them, so they don't have the long lives that G and K stars have. F stars are more interesting already, but they still have a little bit too short lifetime maybe. G and K stars are within our focus, and M stars as well, whereby with M stars we are focusing several challenges, which I will go into more detail later on. So they have very slow evolution, stable habitable zones, but only very late in their lifetime. So there are quite a few challenges. Although M stars are very attractive these days, there are planet hunting missions like TESS and also others who specifically look for habitable planets around M stars, because there you can detect them much more quickly, much more easily. Habitable zones are much closer in. So there are several pros, but we have to be skeptical and careful, and I will talk about that later. So if we want to establish and sustain habitability around the planet, many astrophysical factors need to be right. They need to be in good place, in good shape. I thank Manuel for this slide. I stole it from him, or he gave it to me. Maybe we'll see it again. So we need to take care about the stellar radiation in different wavelength range, particles and CME output of the star, winds and magnetic fields, and planetary magnetospheres. And I will focus on some of these aspects in the course of my talk. So the stellar environment that is shaped by the star itself is very important to consider also in an evolutionary term of view. The activity output I mentioned already for stars is triggered by the stellar magnetic fields. So any kind of star we observe in the universe does have magnetic fields. There is a tiny group that does not have that many, but recently also quiet A stars were discovered to have magnetic fields as well, different ones, but they have them. So we need to take them into account to understand them, to understand what's going on inside the stars in terms of stellar magnetism, to be able to understand their output. And within the different types of stars, we are focusing, or we are confronted with the globally strong and stable fields of AP and BP stars, but these are not in the center of our attention. As I mentioned already, they are too shortly lived for likely too shortly lived for habitable planets around them. Then totally different effects on the surface of stars we see for solar type, for G and K stars, where you have locally strong and dynamic fields of which change a lot, which create a lot of output. I will go into more detail on that later. And for M dwarfs, we again see a very different M dwarfs as soon as we are really late type, when they are M5 and later. They start to be fully convective, and they again produce very different kinds of stellar magnetism. So they again have very globally organized, strong magnetic fields, which are less complex than the one of solar type stars. But again, different from the hot star fields of A and B stars. So magnetic fields are created within solar type stars. I'm focusing on that now, by the so-called alpha omega dynamo. That is an interaction of rotation and convection inside the star. And again, to show you, in cool stars, we have more or less big radiative core, a convective layer outside, and these two layers are rotating differentially. So the core is rotating more quickly than the shell. And this interaction creates a so-called alpha-omega dynamo, where the magnetic field is produced and triggered and kept on. This will get important again later on when we talk about rotational evolution. This has a lot to do with the structure inside the star. For K stars, the convective envelopes are getting thicker and thicker until late type M stars, which get fully convective from spectral type M5 on. To show you the other range of the HRD on a sketch for the Sun again, a radiative core and a convective layer that is getting thinner and thinner towards A stars. A convective core starts to evolve in the center of the star, which is again getting bigger, and the outer convective, very thin convective layer is getting smaller and smaller for B stars. We do observe magnetism for these stars as well, but it has very different properties than magnetic fields for the Sun for solar type stars. Triggered by these magnetic fields are all kinds of activity signatures, solar surface and spots. And if you have a look into the interior of the Sun, the radiative core and the tachocline, the shear layer between the convective layer and the radiative core, you see that flux tubes are created. And sometimes, if the field gets strong enough, these flux tubes diffuse onto the surface. This is where the spots on the solar surface are created, the dark spots, as the convection is stabilized here and the areas are getting cooler in where the flux tubes are getting outside of the surface. And this is changing a lot with solar activity level. So if solar activity level is at maximum, we have more spots. And if it's at minimum, the global field is getting bigger, but the spots are getting less. So that has a lot to do with the activity cycle of the Sun. And the alpha-omega dynamo driven by the tachocline is working inside to produce this magnetic field. So as I mentioned already, differential rotation is an excellent mechanism that is producing magnetic fields organized on large spatial scales. And the flow with chaotic trajectories, which is produced by turbulence, for example, that can act at a small scale as well. And when rotation is present, a turbulent flow in a stratified environment can produce a large magnetic field. So this is what essentially is going on inside a solar type star or K stars. These magnetic fields produce flares, coronal mass ejections, high energy radiation in UV, EUV, and in X-rays. They also produce stellar winds. And what we can study and what we want to study by understanding magnetic fields and their output in more detail is radiation-atmosphere interaction of the star and the planet, magnetosphere and wind interactions, and the whole magnetosphere-atmosphere system in the long run. So magnetic field evolution and stellar evolution has a lot to do with rotational evolution and the according activity evolution in the lifetime of a star. If you have a look at this slide, that's a sketch again, a solar type star, a very young star with a lot of spots all over the place. And as it's getting older, time is increasing, the spots are getting less and less, the star is getting less and less active and producing less and less activity output. A planet around such a star is evolving from the very beginning on together with the star. And as you can imagine, it's very important how the Sun in the past looked like. How the planet in the end could evolve and produce an atmosphere, get rid of an atmosphere, and so on. This is something that will be addressed in future talks, in Manuel's, for example, I think. But the evolution of a star, that's the point I want to make now, is very important for the co-evolution of the planet around the star. And as it's changing a lot, we really need to take care of that and also get the history of the star if you want to know the history and the evolution of the planet around it. So if we are having a closer look at the rotational evolution of stars, of solar type stars, what you see here is plotted Rossby numbers against LX, L-bond, so activity or values in X-ray in relation to bolometric luminosity. And you see that if you plot observed stars that at a certain rotational level, fast rotating stars here, slow rotation here, you see that the stars, the very quick rotators, will reach a certain saturation level in X-rays, and then as they age, as they rotate, start to rotate more slowly, also the X-ray activity increases, which is as well, of course, very important for the planet surrounding these stars. The sun is imprinted here. So not only rotation is decreasing, but also X-ray levels, which at the beginning are very high, spots are in high numbers. Also the X-ray levels are decreasing, which is of course important for the planets around them. The same holds true for the large-scale magnetic flux. So also the large-scale magnetic flux of aging stars is correlating with the rotation and shows a saturation in the beginning. So stars, when they rotate quicker and quicker in the past, or when they are younger, so to say, they don't necessarily increase the magnetic fields endlessly, like it is the case for X-rays, but there is a certain saturation level. And as they age at a certain point, also the large-scale magnetic flux is going down, together with the age and the rotational evolution of the star. So if you want to attack that and address that in a better statistical way, and that is work that was done by Colin Johnston in our group, we can plot, for example, stars with different stellar masses and a rotational period, plot in days here. And you see that for specific masses and for specific rotational periods for that age, which is very young, and then the distribution is getting older under quotation marks, you see that we have rotational periods all over the place. So initially, any star, any solar type star can have any kind of rotational period. And as the stars age, they cluster together towards the shorter periods. Let me show you a short movie on that as well. So we are starting off with a stellar distribution where stars have the same age of 100 megayears. And as age is increasing, denoted in this number here, you see that the rotational periods also decreases towards a certain, increases towards a certain value, and at some point the stars all get together more or less. And this already happened for our sun, by the way. So the sun is rotating quite slowly already. It's a middle-aged star, and we cannot trace back how it really rotated in the past. So if it was a fast or slow rotator, which would be very important for us, and we try to find out more on it. But even for the sun, we cannot really tell if it initially was a fast or slow rotator, which would be, of course, very interesting and important to us, because then we would know which systems do work, like the Earth and the sun could evolve together to a habitable planet, luckily, as we all know. So if we want again to put this into rotational evolutionary tracks, for example, we have the fast rotators on this track, again age against rotational period, intermediate rotators in green and slow rotators in red. And if we analyze the rotational evolution or plot the rotational evolution track against the X-ray evolution of a star, we see that something I kind of mentioned already, that for the slow rotators, so the ones that started out with a very slow rotational period, the X-ray evolution is taking a very different path than the one for the fast rotators. So there's a big difference in activity output and X-rays and any other kind of likely also CMEs, flares, around the fast rotators than it is around the slow ones. And the intermediate rotators here in green are somewhere in between. So we are facing non-unique activity ages. And of course, I guess you can imagine that this makes a big difference for planets around the different solar type stars. And what needs to be mentioned as well, exactly this period is the important period for a star-planet system to evolve into a habitable or non-habitable one, as the formation of the planetary atmosphere is happening exactly in this period. Crust plate tectonics are coming in, oceans are evolving. So it's really crucial for a planet around a star, what happens during this time period. So we really want to find out more how these different factors are influencing planetary atmosphere, evolution, erosion in different ways. And we can also study how the different rotators erode atmospheres in a different way, but this will again be shown in Manuel's talk, if I remember correctly. So I'm referring to his for tomorrow. And I mentioned X-rays already, and we also need to talk about energy output in different wavelengths, of course. So we talked about rotational evolution. Stars are starting out with different rotational periods, getting older, having very different scales of output depending on their initial rotation rate. And we can and need also to consider this output in the different wave bands. I'm showing you here, for example, to really see how different it can be. Pictures for the sun in the optical wavelength range, the photosphere around 6,000 K, lower layer, the photospheric layer of the sun, then a little further above where the atmosphere is getting heated up already by magnetic fields, magnetic reconnection processes we do not fully understand yet. So the chromosphere just above the photosphere having already around up to 10,000 K. The ultraviolet sun looks a lot different from the optical sun. We already see plage areas, spots. We see it in the optical as well, but these plage features and the magnetic field features we do not really see in the optical sun. Then the transition region in EUV, where the outer layers are heated up to 50,000 K already. You already see flare signatures and CMEs possibly that get out when flux tubes are opening. And then again the EUV sun heated up to 600,000 K already, again a higher layer. You see a lot of activity output as well, and again. And the 2 million corona of the sun in X-rays, where the same picture, the same stage, is showing a lot more activity, a lot more radiation, which the planet is facing as well, of course. And especially when the sun was younger, when solar-type stars were younger, they show even much more of this energy output in X-rays, as I mentioned already. So if you really want to take into account the effect that a star, the sun, has on the planetary atmosphere, we also need to take into account the different influence of the different wave bands in the optical photosphere, active, inactive, UV, and chromosphere. And what a project that a master student of us was working on is put together all the different signatures for a spectrum from a quiet area, from a spot area, and from a plage area, for example. And for this work, we need filling factors of the different components to denote them as a function of stellar activity level, like S index or Lx to L-ball. And what she did in the end was construct spectra for the different contributions from the solar surface, from plage, faculae, and hot faculae areas, umbra, penumbra. And you see that on this plot, wavelength against irradiance, the different components of the different areas on the surface of the sun, they have, or of solar-type stars, they have quite different spectroscopic signatures, especially in that wavelength range. Whereas in other ranges, they are quite similar. So we need to take into account the different levels here. And what she also did was putting together synthetic XUV spectral irradiance from these solar components for a set of young solar-type stars, Ikedrae, Paivonouma, Beta Coma, and the Sun in this case. And Ikedrae is a very active star, the youngest star in the sample actually. And you see that the irradiance for Ikedrae is significantly higher than for the Sun, for example. The Sun denoted here in yellow, and then two other stars, Paivonouma and Beta Coma, who are slightly older than Ikedrae. So you really can follow the age sequence in that wavelength area in the spectrum as well. And you need to take it into account because different Wavelength bands have different influences on atmospheric signatures of planets, so they erode different layers of the planetary atmosphere, said in simple terms, and cause different chemical reactions in a planetary atmosphere. So what I did not mention yet in a little more detail are flares, superflares, and coronal mass ejections. So rotation is important, activity in different wavelength bands is important, and flares, superflares, and anything need to be taken into account as well, as far as we can do that, for example, with the spectra I just showed you. But just to give you a little more details on flares, superflares, and coronal mass ejection, what can be done, what cannot be done from the observational point of view. I will show you in the next few slides. So coronal mass ejections are triggered by magnetic reconnection processes. This is work that is a lot done by Rachel Austin and Shibata. And they appear when during sudden releases of magnetic energy stored near sunspots. So you have flux tubes diffusing up to the surface. When they open up, CMEs can occur. And superflares were already observed in other stars to have 10 to the 33 or 39 erg, which is quite a bit more than the sun usually shows in flare signatures. They seem to be less frequent on solar-type stars, but the largest flares are 1 million times more energetic than the largest solar flares. The maximum energy is correlated with the rotational period, not surprising likely, and superflares seem to occur more frequently on faster rotating stars. It's not correlated, sorry. Solar flares are sometimes associated with CMEs and can cause geomagnetic storms. And we can study stellar flares in quite a bit of detail. They are observationally accessible in quite a good way, but CMEs are not. There have been quite a few attempts already to detect CMEs on other stars, but there was not any conclusive detection yet. Just another nice picture of a flare when we have a look at the X-ray sun with the Yuko instrument. You see that the sun is flaring. You see again the nice flaring activity signatures on the surface of the sun. Discoveries of superflares were also done with Kepler data. I just wanted to show you some current observational investigation that is going on by colleagues from Japan, where they, by analyzing a lot of Kepler light curves, high quality space data, they discovered a lot, like more than 1,000 superflares of very high energies in around 300 solar-type G stars, so G-type main sequence stars, which is really a lot. And they analyzed data of 30-minute cadence and saw flare signatures that are huge like this, for example. And the flare energy is the radiated energy in the white light range and calculated by assuming a 10,000 K black body radiation. But this is just to show you other stars. G-type stars seem to flare a lot, and a lot of them also seem to have a lot of a very high frequency of superflares going on. And we, of course, ask ourselves as well, how is the sun behaving in this respect? But for the sun, the likelihood seems to be very low that superflares are occurring more often than one time in 1,000 years. But of course, we cannot exclude that we will also face another superflare. I mentioned already, observing flares on stars is easy, and we want to do that because we want to get statistics. We want to find out how often flares are occurring on other stars to be able to study their influence on and model their influence on planetary atmospheres. They can be studied via coherent radio emission in long wavelengths for the sun and for stars. Radio gyrosynchronous synchrotron radiation wavelengths can be studied, can also be done both for the sun and the stars, like optical UV continuum signatures for flares, optical emission lines, far UV emission lines, EUV soft X-ray, and non-thermal hard ray X-ray emission. Can be done for the sun, wasn't done for stars yet, or wasn't achieved yet. So that needs to be clarified. But for CMEs, it is a lot more difficult. So for the Sun, we know there are CMEs, they affect us, they affect our atmosphere. But for stars, we don't know how they behave in comparison to the Sun. It is likely that they are not so different. So Thomson scattering measurements via coronagraphs are possible for the Sun, but not for stars. Type 2 bursts, which are a signature for CMEs for the Sun, can be done for the Sun, but have not been detected yet for stars. There have been several attempts, but no detection so far. Non-thermal emission, scintillation of point radio sources, and so on. So a lot of detection methods that are possible and more or less easy for the Sun it was not possible yet to do it for stars. So we don't know how stars behave in terms of CMEs yet. An investigation I wanted to mention, also done by Rachel Austin and her collaborators, is a GVLA, a radio telescope, and Apu simultaneous measurements of M dwarfs. And there they observed a lot of flaring and activity signatures, but during their 20 hours observations and overlapping radio and optical data, they still did not identify any type 2 bursts. So even a very intense search for flares or for CMEs in connection to flares was not successful so far. But the work is continuing, and it might also have something to do with the type of the stars, like the SVs are M stars, which have quite strong magnetic fields. So we were talking about output in different wavelengths, rotational evolution, flares, CMEs. Winds are important as well, of course, which are also launched by the magnetic field. We discussed in the very beginning. And I won't go into any detail here because this will also be covered in another talk. But just to show you shortly how important the stellar wind that is launched by the magnetic field also is, and very likely is, in terms of particle outflow and effects on the planetary atmosphere. Here's a picture of the Sun, of the solar wind signatures made by Ulysses, where observations were done during solar minimum. And you have outward and inward flows, and you see that in comparison to the solar maximum, there is a lot more ongoing, a lot more chaotic structure, and a lot more wind launched in any direction around the Sun. More details on that in another talk, as I mentioned. So if you want to understand stellar activity, we need to understand the magnetic fields. I hope I made this point already. And I wanted to, of course, also tell you something on how to detect and how to analyze magnetic fields, because this is crucial if we want to get more understanding and study them in more detail. There is a technique, the so-called Zeeman Doppler imaging, where based on big telescopes and spectropolarimeters, we can observe a star having a magnetic field that is rotating. This is a schematic drawing, of course. A star with a very strong dipolar field to make the signature stronger and easily visible, inclined by 45 degrees, with an I of 10 kilometers per second. And as you see, as the star is rotating, magnetic field lines are pointing outwards and inwards, north and south pole. These so-called Stokes parameters are changing a lot. We have the Stokes I parameter to the upper left, V, Q, and U on the bottom, and these are parameters telling us how the magnetic field geometry is changing. V is a measure for the circularly polarized light that is polarized by the magnetic field, and depending on the strength and the shape of the signature, we can get some information on the geometry of the field by inverting these line profiles into stellar images. So what we see from the star is only these profiles in the best case, but not this picture. This is what we calculate via doing the Doppler imaging procedure, and this is how we can, from a very good observational set, we can determine magnetic field geometries. This is currently being done and was done by many people, by us as well. So Deshna is also working on that, sitting here in the audience, for quite a number of stars. And the project we are currently working on is doing the mapping and then field extrapolation and wind modeling for a sample of young solar type stars, Pivonuma here again, where you see data and Doppler imaging, magnetic Doppler imaging results from 2 different epochs. The star was observed in 2007 and in 2015. And based on the Stokes parameter changes I was just showing you, we reconstructed the surface field geometry in both observational periods. And you see that for 2007 we had quite a simple geometry. Negative magnetic field on the pole, some positive components here. And if we compare that to the result in 2015, you see that a lot more complex patchy structure is going on in that year. And for this star, we still need to find out if there is maybe a polarity switch going on, as the sun is already also showing it, and other stars are showing it. So that was observed and analyzed already. But for this star, we don't know yet. It's continued to be observed. And similar work is done for a set of other prototypical young solar type stars. Ikedra, we had it already before, having modeled the spectra in different wave bands, X-ray, EOV, H and PAC, Pi1 UMA, Pi1 Oribi Ceti, and Kappa 1 Ceti, spanning an age range from very young to older ones, approaching the or being on the suns already, and also having ages already where life on Earth or life around such a star could have started already. So we try to cover a good age range of young solar type stars to be able to see how activity, how magnetic field, how all the other structures develop in order to be able to then do the wind modeling around the stars. So the magnetic fields I've shown you for Pi1 UMA, and here in this case for Kappa 1 Ceti, they can be extrapolated, and the winds, based on a code we are using in collaboration with people from NASA, the wind modeling can be done, and we can then study in more detail how the wind affects the planetary atmospheric erosion. This is important to be able to do because stellar winds cannot be detected directly. So we need to somehow model them and try to get as well-determined conditions as possible around young solar type stars, for example, to get a clue on how the Earth or what conditions the Earth was facing in the past. So this mapping work is done by quite a few people meanwhile, and there have been several observational sets together, statistics were done and put together. And let me show you a plot that stores a lot of information. And there are, again, we've plotted, they have plotted rotational period against stellar mass. And the color symbols shows if a magnetic field, so this is all information about magnetic fields, statistical information about the magnetic fields of these mapped stars. The color shows us if a magnetic field is more poloidal or toroidal, the dominant component is more polar-like or toroidal-like. The shape of the symbol tells us how axisymmetric or non-axisymmetric the magnetic field is, so if it's simple or complex, more or less. And the size of the symbol denotes the strength of the field. And if we again have a closer look, we see that for the fully convective M dwarfs I was mentioning in the beginning already, WX UMA, for example, here, they are quite quickly rotating and have very strong but very simple fields. So simple shapes, big symbols, more poloidal components, whereas for the more solar type stars, the higher masses, we have more complex fields, and thus they are rotating more slowly and slowly. The fields are getting weaker and weaker, and we see quite a nice evolution and quite a nice picture together with stellar mass and rotational period. So we can get a statistical clue on how stars are behaving in terms of magnetic fields. There are always exceptions, of course. I won't go into those now, but we have quite a good idea already how magnetic fields possibly evolve together with age and with stellar mass. So what can be done already in the end is, based upon the maps I was showing you, doing magnetic field extrapolations, wind modeling, and put this into context of the plot I showed you before and find out if a star is really fast rotator with a lot of X-ray output, try to cover this area in a very good statistical way and try to get as many boundary conditions as possible for our estimates, how different conditions influence planetary atmospheres in different ways. I'm telling you a little bit more on M-dwarfs and their issues with habitability, non-habitability. They are one of the exciting subjects currently in terms of search for habitable planets around them. And just to mention some characteristics and to put them into context with solar type stars, is showing you this plot, time again against Lx to L ball. And we have plotted different tracks for different stellar masses, 0.1 solar masses, 0.2 and so on, 0.3 up to 1 solar mass. The sun should be around here. And we see that in terms of X-ray level, they are starting out with quite comparable levels. But M-dwarfs are especially the very late type M-dwarfs, they are staying a lot more, they are staying at a higher X-ray, at the big, initially high X-ray level for a much longer time, in contrary to solar type stars, where the X-ray activity level is going down quite quickly with time. Because I'm mentioning this also because from M-dwarfs you might often have heard already or will hear in the future that they are said to be very active and have to have very high activity levels, which is actually not true. They don't have higher levels than solar type stars. They start at the same levels, but they stay active for a much longer time, which likely can cause a very harsh environment for planets around them. So even if we have another look at another wavelength area in the near UV, even there the most active M-dwarfs, like ED Leo in this case, they show lower near UV in their habitable zones, and only in the far UV they are getting, the most active M-dwarfs are getting more luminous than the sun. So also here the activity level is not really higher than for solar type stars, but it's staying up quite a bit longer. In terms of flare numbers, flares important indicate or important triggers or important effects to consider when talking about habitability. If we have a look at the flare rates comparing solar type stars, again Ikedraw, a very young solar type star, Abidor, a little less active, ED Leo, CN Leo, going towards M-dwarfs, Kappa 1 Ceti with increasing age. You see that for the young solar type star, if we have a look at the XUV flare rate above a given threshold, it decreases a lot, like say from 10 to 3 to 0.6 and 0.01 with decreasing mass, so solar type to M-dwarfs. And the overall emission decreases quite a bit as well. And also with age, we have a decrease of flare rates from 10 to 0.2 for a given threshold per day, for example. So solar type stars are, young solar type stars in particular, are flaring more than M-dwarfs. But what might be an effect that could be important when talking about habitability is that the contrast between the flares on an M-dwarf surface, the stars are much smaller, so in relation the flares might, they stand out more, they show a higher relative amplitude if you compare them to solar type stars. That might have an important consequence for atmospheric photochemistry or life on planets around these stars. So this different relation in flare signatures might be important if we compare solar type stars and M-dwarfs habitability. We should take that into account. So another issue with M-dwarfs is that if we ask ourselves what are the best host stars, is that they have a very long premium sequence evolution. The luminosity decline for G stars is much flatter. What you see here is a plot, again, stellar age against stellar luminosity for F stars, G, F, another F5 star Sun, K5, M1, M5, and M8. So decreasing temperature and masses. And you see that the luminosity evolution with age for F stars and solar type stars is quite flat. So there's a decrease, a slight increase again, but it's more or less flat. So a planet around a solar type star is facing very comparable conditions throughout its lifetime in terms of luminosity. Not in X-rays, not in other activity signatures, but luminosity is not changing so much. Which is not at all the case for M dwarfs. So if I have a look at the M dwarfs, around M8 for example, or M5 already, you see a steep luminosity decline, and then it's getting flat a lot later, which also means that the habitable zone is shrinking. You don't see it very well here. That's a circle, that's another one. And the star in the center is the star, and this is the habitable zone extent around the young M dwarf. And later on, at this age, you have the habitable zone with decreasing luminosity much further in, so the zone where water can be liquid on the surface of a planet around this star. So there is really a shrinking habitable zone around M dwarfs, and I personally would not be able to figure out if systems could exist that where a habitable surface survives out here, survives as long as, or a planet here, in here can survive as long as it's getting into the habitable zone together with the stellar evolution later on. So this is really a timescale issue that is not solved yet, and the host star in principle should stabilize before the ocean crust formation. We do not know at all if this is possible or not in such systems and such configurations. So in contrary to G stars, we are confronted here with changing extent or changing positions of the habitable zone with the lifetime of the star. So again, showing you the plot from before, including M dwarfs, age, LX to L ball. So X-ray level with slow rotators, intermediate and fast rotators. And if we compare that to a similar figure that is denoting M dwarfs, we see again that M dwarfs are staying at higher activity levels for much longer than decline. They decline very steeply. And we just don't know at all how this high magnetic activity level during the first billion years affects a planetary atmosphere, if it can stay livable or not. Or if it can evolve later. It sounds unlikely to me, and we don't know how these harsh conditions really affect the stars, the planets around them in the end, and the atmospheres. So the strong flares, coronal mass ejections, and everything that's going on the stellar surface we mentioned already is affecting the planets on a much closer orbit. So this is also something we need to consider, that the signatures are not stronger than for solar type stars, but the planet is much closer in, which certainly has an effect. Also in terms of magnetic fields, I mentioned already in the beginning M dwarfs, and I'm going into more detail here now. M dwarfs can have very different configurations. When we're going to the very cool low mass M dwarfs, we can have magnetic fields up to 6.4 kilogauss, which is a lot more than for solar type stars, dipolar configurations, activity underneath. And these might of course also cause very harsh for planets around their atmospheres. And this is again another plot to show you how different magnetic field signatures for M dwarfs can be. On the top you see DT Virginis, an early M dwarf, still having a radiative core. If you remember the slides from the beginning, having more solar type magnetic fields with a tachocline alpha omega dynamo, rather weak and complex magnetic field. And as we are getting to later M dwarfs, GJ51 for example, we again see these are positive magnetic field negative positive magnetic field components. The fields are getting quite a bit stronger, up to 1.6 kilogauss in this case, or up to 5 kilogauss, changing a lot with time as well, and being much more simple but much stronger. And I think we can all imagine that conditions around such type of stars are very different from conditions around solar-type stars. This is again a comparable diagram, just to shortly show you, only for M dwarfs. So again, very strong fields, simple geometries, but at the same time exceptions, weaker fields with stars of similar configuration, similar mass, and similar rotation periods. It's not clear yet why this is going on, what the mechanism behind that could be, but just not to forget about it and to mention. We do not understand magnetic fields fully yet. It will still take some time. Another effect, a very interesting study I wanted to mention that was done by one of our postdocs in our group as well, Kristina Kislyakova, is the strong magnetic fields that could also cause induction heating in planets around them. So imagine there is a star with quite a strong magnetic field, simple configuration, planets are surrounding it in quite close in the habitable zone, and the planet is then still within the magnetic field of the star, more or less. And this magnetic field can cause or can induce then additional heating in the planet, which will make it difficult to let the crust solidify, which is of course very important to get a habitable planet. And it can also lead to increased volcanic activity and even to magma oceans in some extreme cases. So it is possible, according to studies, that the surface of such a planet around a M dwarf with a strong magnetic field can maybe never solidify in the end. So, to finalize, facts and questions to address and maybe to give you along the way some things I thought I would like to summarize and mention is that stars with stellar engine is the driver of planetary environments in terms of how the planetary atmosphere is eroding. I hope I got this message through, that the star in the center of the evolution and the co-evolution with the planetary system is really important when we talk about habitability. The rotational evolution together with the magnetic field evolution and activity evolution matters a lot. And if you want to understand habitability of a planet, we need to understand the co-evolution of the whole system. If we compare solar-type stars, habitability around solar-type stars and M dwarfs, they have comparable activity levels, but M dwarfs are active for a much longer time. The flare contrast in M dwarfs might be important though. So in relation, the flares are standing out more for a planet surrounding an M dwarf. And it is not clear at all how this affects the photochemistry of an atmosphere. Then we can of course ask the question if fast rotating stars offer better conditions for planets in the habitable zones, or for example if planets, but that's discussions that will come on will be in later talks as well. If it might be important that fast rotating stars can erode massive hydrogen envelopes more quickly or in a better way, might be necessary for super Earth planets like, for example, so that the secondary atmosphere can evolve on the planetary surface. So we just don't know yet if it's necessary to have a fast rotating star in the beginning, an intermediate or a slow rotator in the end. There are hints already, there are studies ongoing, but we don't know really yet what condition is the best one to produce a habitable system. And it might also be that there are a lot of different parameter combinations like fast rotation, a bigger planet, whatever, that could make it possible to make an environment around a star habitable or not. And we still don't know yet if if the system like the Earth, the Sun and the Earth system is unique, or if we have many different possibilities, grids where habitable planets can develop. So we don't know yet, but I'm very confident that we'll find out in the next years, next decades, hopefully. I'm quite sure within your science lifetime, as you're all very young still, most of you. So we don't know yet, but I think we will find that out in the near future, also with the help of you in the future studying astrophysics, astrobiology, whatever subject you choose in relation to habitability of planets. Thank you.